Welcome back. We will continue studying about solutions about ordinary points. So we're going to consider another example here. It's about power series solutions of the given linear differential equation of order 2. So this is our equation. So here we are asked to solve this or to find this power series solutions. So as you see here, this is second order and it's already in standard form. Our P is X, right? P of X is equal to X. So from here, actually, there are no any singular points of this differential equation, right? It doesn't have any singular points. That means that theorem 6.2.1 guarantees two power series solutions centered at 0 that converge here, right? That means that any point on the number line is regular point. Actually, we can find this power series solutions of this form if it is centered at 0. N equals 0 to positive infinity, c sub n times x to the power n. Okay. Actually, the center of the convergence can be anything, but here we want 0 to be the center of this convergence. Okay, so now suppose that this is one power series solution of the given differential equation. Okay, so now we're going to substitute this into here. Before this, we need to differentiate twice, right? If you differentiate this once, n comes to the front. Here we have n times c sub n times x, and differentiate one more time, we will get this, right? N times n minus 1. Here we have the coefficient x to the power n minus 2, right? So when n equals 0, when n equals 1, actually those terms are 0. That's why here our index is starting with 2. Now I need to substitute this into this equation. So y double prime equals this. So here we have y double prime plus xy. On the right hand side we have 0. Y double prime is power series representation is this. The substitute here. Plus here we have x times y. Our y is this, right? And put it here. So the first step, x is outside, so I bring this inside the sigma notation. Okay, so here is we don't make any change to this term, to the thing. Plus here, if you bring this x inside, x times x to the power n. Here we have x to the power n plus 1. So next task here is we try to represent or express these two power series as one power series. To do this one, actually, we need to have a common factor. We try to have the same x component here. Here we have x to the power n minus 2, x to the power n plus 1. They're different. And also this indices right here, we have n equals 2 is starting with 2. Here is starting with 0. So by doing some manipulation or re-indexing, I can actually change this, this index into the same value so that the index starts from with the same number, right? For example, let's say here, when n equals 2, the first term of this power series is, here we have c sub 2, 2 times 2 minus 1, that's equal to 2. And here we have x to the power 2 minus 2, that's equal to 0. So the first term does not have x, right? So that means that we can just take this out. And the first term has x to the power 1. But here, when n equals 0, here we have 0 plus 1, x to the power 1. Right? Now, this actually variable parts are the same, right? So that I can just take this out, and also we have to re-index that so that this index starts with the same number. So here, if we do so, the first term of this power series is 2 times c sub 2 when n equals 2. But now, after that, this starts with 3, right? So when n equals 3, and here is starting with 3, here is starting with 0. So now I want this power series, its index to start with 1. Okay, and also this one, we wanted to start with 1. To do so, how actually, what change I should make to this index? Here, to make this actually start with 1, right? Here we have n minus 2 equals 0. I will just do this relabeling. Let's say k is equal to. So when k is equal to 1, this should be equal to 2, right? So that means that let's say k or n, k equals n minus 2 plus 1, so n minus 1. Okay. If it is so, when n equals 2 here, right, 2 minus 1, k will be 1. So from here, n is equal to k plus 1. So I will do this, I'll make this substitution. In a similar way, here we have n plus 0 is equal to 0, right? If I just shift 1 unit to the right, at the time, here we will have k will be equal to n plus 1, right? At the time, k starts with 1. Because you see here, when n equals 0, right, 0 plus 1, k equals 1. So wherever I see n, I will just substitute k minus 1. Oh. So here we have n equals k minus 1. Doing this substitution, as here, where we have n here. Here we have n minus 2, right? So if you substitute here instead of n, k plus 1, take to the right hand side, k equals 1. K starting with 1, right? Here we have c sub n. What is n? K plus 1. So here we have, actually, here we have 3, right? This thing is already out. Here we have n equals 3, right? So here we have n equals k plus 1. And if you substitute n minus, for n, if you substitute k plus 1, so it will start with 1, right? Here we have, actually, now here we have something like this. N equals 3 to positive infinity, c sub n times n minus 1 times x to the power n minus 2, right? So instead of n, we just substitute k. Here we have n equals 3. So to be actually with, for k to start with 1, right? So here, 2 units. So we should write here k equals n minus 2. At that time, n will be k plus 2. You see here, when n equals 3, right? If it is 3, k will be 1, because 1 plus 2 equals 3. So for k, we need to substitute n minus 2, or for n, we need to substitute k plus 2. So here, k starting with 1, c sub n. What is n? K plus 2. Here we have c, k plus 2. What is n? K plus 2. So here we have k plus 2, right? And n minus 1. N is k plus 2. K plus 2 minus 1. That is k plus 1. Plus, how about here? N equals k minus 1. So here we have n. That is k minus 1 times x to the power. What is n plus 1? N plus 1 is k. Okay. So now it is identically equal to 0. That means that this 0 means that is a 0 polynomial, right? So actually, for these two things to be equal for every value of x, all their corresponding coefficients and constant terms, they must be equal to each other, right? Here, what we have here, actually here we have 2c sub 2, right? Here we have 2c sub 2 plus when k equals 1, x to the power 1. Here we have something, let's say this capital C sub 1 times x plus capital C sub 2, x squared plus dot dot dot. On the right hand side, we have 0 polynomial. That means that here we have 0 plus 0 times x plus 0 times x squared dot dot dot, right? And if you're claiming that these two things are identically equal to each other, that means that all their corresponding terms must be equal to each other, must be exactly the same. That means that from here to c sub 2, right? What is the constant term? 0. That means that here we have c sub 2 should be equal to 0. Now I know this coefficient, right? And how about other stuff? Actually, they are connected to each other by this recursive formula, right? Now from here, if I take this to the right hand side, it becomes minus, and divide both sides by this, right? I will get this expression. Okay, this is how these coefficients are connected to each other. So now substituting some suitable values for k, we can determine the values of these coefficients. For example, if k equals 1, right? Substitute here, if we have c sub 3, 1 plus 2 is 3, and 1 minus 1, it is c sub 0, 1 plus 1, it is 2, 1 plus 2, it is 3, and here we have minus, right? How about k equals 2? If k equals 2, substitute here again, 2 minus 1, it is 1, here we have 3 times 4, here we have 3 times 4. If k equals 3, again substitute here, if it is 5, right, c sub 5, it is 3 minus 1, it is 2, here we have 4 times 5, because 3 plus 1 is 4, 3 plus 2 is 5, okay? And since we have already actually found the value of the c sub 2, right, in the previous slide, so this c sub 2 is equal to 0, 0 is divided by anything, here we have 0. So this coefficient is equal to 0. If k equals 4, we get c sub 6, right? If it is 4, here we have 4 plus 2, that's equal to 6. And 4 minus 1, here we have 3. 4 plus 1, it is 5. 4 plus 2 is equal to 6. And c sub 3, we have already calculated here, right? That's equal to minus c sub 0 over 2 times 3. And substitute here, so we will have here, with this minus, that's plus, 2 times 3, and here we have 5 times 6, here we have c sub 0. So in similar way, we can actually find c sub 7 when k equals 5, right? Substitute here, we get this expression. When k equals 6, that is 6 plus 2, here we have 8. 6 minus 1 is equal to 5. What is c5? c sub 5 is equal to 0. 0 is divided by this number, that's equal to 0. Right? C sub 7, if it is 7, 7 plus 2, that is 9. And C 7 minus 1, that is 6. 8 times 9. C sub 6, from here, right? From here, we know what is C sub 6. And substitute here, right? That's equal to 2 times 3 times 5 times 6 times 8 times 9 times here we have C sub 0. How about C sub 10? If k equals 8, we get the value of this coefficient, that is c sub 10, that is k equals 8, 8 minus 1, it is 7, over 8 plus 1, it is 9, 8 plus 2, that is 10, right? And c sub 7, here we know this, right? And just substitute into here, so we will get here, what is this? 1 over 3 times 4 times 6 times 7 times 9 times 10, and here we have c sub 1. Okay, and also k9. In this way, we can actually determine the value of c sub 11. So if k equals 9, here we have 9 minus 1, c sub 8. And from here, c sub 8 is equal to 0, right? And that's why is equal to 0. And it will continue. Now here we try to get the pattern. We try to see find a pattern here. And also, if you notice here we have two arbitrary constants, right? Number one is c sub 0, because it's not dependent on anything. It can be anything. And the second arbitrary constant here is c sub 1. And also, actually, it is natural because we know that the second order linear differential equation, it must have two linearly independent solutions, right? Now, in this way, after finding this coefficients, c sub 0, c sub 1, c sub 2, c sub 3, all of this, now we need to substitute into our power series, right? Because we're looking for the solution of the given differential equation in this form. That is, what is it? That is sigma, right? Here we have n is equal to 0 to positive infinity. And here we have c sub n times x to the power n. That is assumed solution. We suppose that that is the power series solution of the given differential equation. So when n equals 0, right, c sub 0 times x to the power 0, that is c sub 0 constant term. If n equals 1, c sub 1 times x to the power 1, the second term. N equals 2, the third term, and blah, 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 right? So now if you substitute those, that we actually calculated the values of these coefficients. C sub 0, it is arbitrary constant, it can be anything. C sub 1 also, it appears, right? We cannot determine the given conditions. That means it's also arbitrary constant, it can be any constant number, plus. And C sub 2, And we know that it is equal to 0, right? C sub 3 is equal to this. C sub 4 equals this. C sub 5 is equal to 0. That's why we don't have x here. C sub 6 is equal to this. And C sub 7 is this coefficient. C sub 8 is equal to 0. C sub 9 and C sub 10 continues, right? So now, as you see here, we have two arbitrary constants here. That is C sub 0 and C sub 1. So I can rearrange this and just write it as something like this. I can just write it as y is equal to C sub 0. And here we have something, let's say y sub 1 of x, right? Plus C sub 1 times y sub 2 of x, right? When I do so, here we have this thing. So that is, when we just write in this form, in the previous one, just take the C sub 0, all the terms which has actually C sub 0 are these terms. 1 minus x to the power 3, x to the power 6, x to the power 9, right? And from here, if you notice this, it is minus, plus, and it should be minus actually. It is minus 1 to the power k. So here we have this sigma minus because the sign is changing. The first one is minus, second one is plus, and the x to the power 9. Here we have x to the power 9. It is minus also here, right? And that's why it should be, this thing is minus, plus, minus, plus, minus, right? And here, what do you notice here? It is 2 times 3 until 3, right? And here we have until 6, 3, 2 times 3 times 5 times 6, right? 2 times 3 times 5 times 6 times 8 times 9. And here, how about the powers of x? It is x to the power 3, x to the power 6, x to the power 9, right? So that is equal to what we have here. Here we have 2 times 3 times, what is 5? 6 minus 5, right? And this one is 6, right? Each time, what do we have here? Here we have 3k minus 1 times 3k. 3k minus 1 times 3k, right? If k equals 1, actually I will get this term, right? And the second one, I get this term. If k equals 2, for example, let's say substitute this, you will get the next two terms. Okay, and how about y sub 2? Again, actually, we'll just take this c sub 1 out, and inside we will have these terms. If you notice here, 3 times 4 is 3, 4, 6, 7, and here we have x to the power 4, x to the power 7, x to the power 10, blah, blah, right? In short form, what are this? It is 3 plus 1, 3 times 2 plus 1, 3 times 3 plus 1, 3 times 0 plus 1. So the powers of x is something like this, 3k plus 1, right? And also here the sign is changing. First it is plus, minus, plus, minus, plus, minus. So we need to have minus here. Okay, and how about these terms? Here we have 3, 4, right? And here we have 3, 4, 6, 7. Here we have 3, 4, 6, 7, 9, 8, right? So that is 3 times 3 plus 1. 3 times 2 times 3 times 2 plus 1, right? Here we have 3 times 3, 3 times 3 plus 1. And that's why it is this form, okay? Actually, these two things, actually, that gives us the power series solutions of the given differential equation. Thank you.